Welcome back students to the part 3 of today's session. In this module, let us discuss about the potential energy of a spring. Consider a mass m which is fixed to a spring and the other end of the spring is fixed to a rigid support. Taking the equilibrium position at the center of the mass, and if the spring is made to extend by applying a force on the mass and then release it, we can see that the mass will execute oscillations about the equilibrium position if the surface is smooth. Let the mass move through a distance x on either side of the equilibrium position. Then the force required to compress or stretch a spring is given by f of x is equivalent to minus kx, where k is a constant called spring constant. This expression is called Hooke's law. The minus sign is just to notate that the restoring force will be opposite to the applied displacement or applied force. We know f of s is proportional to minus x, or f of s is equivalent to minus kx. Let us now discuss the work done to stretch or compress the spring. Work done can be written as integral 0 to x f of s dx if the spring is elongated from equilibrium position to a position x. Substituting for f of s, we get w is equivalent to integral 0 to x minus kx dx. Minus k can be taken outside the integral sign. Integral of x will be x square by 2 within the limits 0 to x. So work done will be given by minus k x square by 2 by applying upper limit minus the lower limit. From a graph between force and displacement, we can see that the area under the line or the graph gives you the work done. So we have seen the potential energy which is stored up in the spring is given by this work done, which is half k x0 square. Now coming to the previous case, the equilibrium position and elongation and compression of the spring is shown in the figure. In the equilibrium position, the force and displacement are 0. When it is elongated, the force is minus k into xm and work done is minus k xm square by 2. When it is compressed, then f of s is equivalent to k into xm and work done is equivalent to k xm square by 2. This is a plot of energy versus displacement. We know when the spring moves about the equilibrium position, it will be having minimum potential energy at the equilibrium position and maximum kinetic energy at the equilibrium position. In a similar way, at the extreme ends, they will be having maximum potential energy and minimum kinetic energy. But in any of the positions, the sum of mechanical energy, that is kinetic energy and potential energy, will be a constant. In this picture, the blue curve represents the kinetic energy and the red curve represents the potential energy of the particle. The black line at the top represents the total energy, which is a constant at each and every point. So we had seen in order to move the spring from initial position xi to final position xf, work done is given by half k xi square minus half k xf square. So a spring has potential energy by virtue of the compression or stretching of the spring. The work done here depends only on the initial and final positions, and hence spring force is an example of conservative force like the gravitational force. So net work done over the closed path of a spring will be equivalent to 0, since spring force is an example of a conservative force. So let us once again discuss the properties of conservative forces. The work done by a conservative force is independent of the path. The work done by it in a round trip is 0. Total energy remains constant. Work done is completely recoverable, and force is the negative gradient of potential energy. Hope you might have understood about spring force and why spring force is an example of a conservative force. Thank you, dear students.